In the 7th lecture in our series in numerical methods in civil engineering, we are going to continue our discussion on error bounds for direct methods. In addition, we are going to introduce iterative methods for solving linear systems. The bounds we obtained till now on the errors due to on the solution of linear systems were due to imperfect knowledge of the coefficient matrix and the right hand side. Basically what we found was that if the coefficient matrix has an error delta A or the right hand side has an error delta B, we tried to find bounds on the errors that will be introduced to the solution X due to the errors in A and B, due to the error delta A in A and the error delta B in B, that is going to result in solutions to errors to the solution X, and we tried to find the bounds on those errors. And what we found was that if the matrix is depending on the condition number, if the matrix is well conditioned, then errors due to in the coefficient matrix and the errors due to the right hand side will be bounded, and it is going to the magnitude of the bound is going to depend on the condition number of the matrix, of the coefficient matrix. Today we are going to talk about errors in Gaussian elimination because of the large number of floating point operations which take place during Gaussian elimination. The accumulation of round off errors due to these floating point operations lead to overall errors in the solution and is therefore a problem. To obtain a bound on the overall round off error, it is necessary to bound the errors due to individual floating point operations. Since the Gaussian elimination process is a combination of a large number of floating point operations, we have to find bounds on the error of individual floating point operations in order to find a bound on the error of overall error due to in the solution due to round off during Gaussian elimination. We consider the floating point decimal representation of a number A. So, suppose we have a floating point number A, how does the computer represent that number internally? Well, the computer almost always represents the number using this format. It represents it as some number m and times 10, depending on the base of the computer. If 10 is the base, then that will be 10 there. If instead of 10 it's some other number, some other base, then that is going to be the appropriate base. So, 10 to the power q, where m lies between 0.1 and 1. So, m is a number between 0.1 and 1 and q is an integer. So, m is known as the mantissa and q is known as the exponent. So, this is how the computer represents any floating point number A. But in reality, the computer cannot represent m up to infinite precision, because the computer has finite precision. For instance, if the computer rounds off floating point numbers to t decimals, then A will not actually the computer will not actually be storing A, it will be storing an approximation to A, which is denoted by A bar, and the approximation arises because m is only the computer only stores an approximate representation of the mantissa m bar, which is rounded off to t decimals, given that the precision of the machine is t decimal digits. So, m bar is the approximation of m which is stored in the computer. Hence, the bound on the absolute error in the mantissa m is given by m bar minus m, which is lesser than or equal to half 10 to the power minus t, which this we have obtained in a previous lecture. So, the error is bounded, the round off error is bounded by half into 10 to the power minus t. That was the bound on the absolute error in the mantissa. If we look at the relative error in A, that is given by A bar minus A by A, which is by definition the relative error. So, this has got to be less than or equal to m bar times 10 to the power minus q minus m dotted with 10 to the power q m dotted with 10 to the power q. That is simply because m bar minus m is less than or equal to half 10 to the power minus t. Sorry. So, we can write that as this is the m bar minus m dotted with 10 to the power q divided by m bar 10 to the power q is less than or equal to half 10 to the power minus t. 10 to the power 10 to the power q 10 to the power q cancels out. This is we know is less than or equal to half 10 to the power minus t, and since mod of m, if we go back to the previous slide and see, m is lesser than or equal to 0.1 and greater than or equal to 0.1, less than or equal to 1. So, if we replace mod of m by 0.1, this has always got to be greater than that, because we are taking the smallest possible value of m in the denominator. So, this thing has to be greater than or equal to this thing has to be less than or equal to this thing, and this gives me a bound half into 10 to the power 1 minus t. Just a correction, this should not be less than or equal to, this is actually equal to, right. So, mod of a bar minus a by a is equal to m bar dotted with 10 to the power q minus m 10 to the power q divided by this, which is equal to this, but this is less than or equal to this, because in the denominator we have replaced mod of m by its smallest possible value, which is 10 to the power minus 1. So, we get this bound on the relative error in A. This limiting value on the relative error due to round off is denoted as the machine unit. As you can see, this is totally dependent on the machine precision t. So, the relative error due to round off in a floating point number cannot exceed the machine unit of the computer, denoted as this whole thing denoted as u. Next, let us consider the effect of operating on two floating point numbers x and y, and let us denote the true result of the operation as x op y and the floating point representation as float of x op y. So, x op y is the true solution, and this is how the computer is going to represent this. So, the relative error since the relative error due to round off is bounded by u, we can say that FL x op y minus x op y is lesser than or equal to mod of x op y times u, which is exactly what we get if we replace a bar here by FL x op y and a, which is the true solution, by x op y, right. So, this is what we get, this is the bound on the relative error. Now, because this is less than x op y times u, we can be sure that there is a number delta with mod of delta lesser than or equal to u, such that this becomes equal. This is less than or equal to mod of x op y times u. So, there must exist a number for which this becomes equal to that, right, and this gives rise to this expression, floating point of x op y is equal to x op y 1 plus delta. So, this is how the computer represents x op y. This is the true solution, and the true solution times this error 1 plus delta is the floating point representation of the result of the operation of x op y. Next, let us go back to the Gaussian elimination, and let us recall that in the kth step of the Gaussian elimination of a symmetric matrix, the elements are transformed as the following: a I k k plus 1 is equal to a I j k minus m I k, where m I k is the multiplier, times a k j k at the kth iteration, kth step, which is equal to a I j k minus aikk by akkk times akjk. And you can see that we are summing, we have j goes from k plus 1 to n, where we have taken advantage of the fact that the matrix is symmetric. Because of round off, the computed values of each of the quantities on the right hand side will differ from their true values and result in additional errors. So, instead of aij k, what is actually stored in the computer is a bar ij k, right, where a bar ij k includes the floating point errors, right, it includes the round off errors. So, it is the floating point approximation, right. So, a bar ij k plus 1 is equal to a bar ij k minus m bar I k a bar k j k. So, here when we compute m bar I k from a bar I k divided by a bar k k, since this is a floating point operation, we introduce certain errors, certain round off errors, right, and this round off error is denoted by 1 plus delta 1. So, this is the error in the computation of m bar I k. Then we subtract m bar I k a bar a bar k j from a bar I j k. So, this operation, this subtraction operation, introduces additional floating point error, which is denoted by 1 plus delta 2. And then on top of let me take a step back. So, this subtraction operation introduces additional floating point error, which is given by 1 plus delta 3, and this operation m bar I k a bar k j k introduces floating point of error, which is given by m bar I k a bar k j k 1 plus delta 2. So, this operation introduces a floating point error, which is given by 1 plus delta 2. This subtraction operation introduces a floating point error, which is given by 1 plus delta 3, and this division operation introduces a floating point error, which is given by 1 plus delta 1. And we are guaranteed that each of these errors must be less than or equal to the machine precision. Now, we say that if we do these operations, then we are going to get these floating point errors, right. So, now instead of that, we say that let us see if we can get exactly the same transformed values at the end of step k by performing the exact computations on perturbed values of a I j. So, the idea is like this. So, we operate on the values that are stored in the computer, and we go through this operation, and we end up with additional errors due to which are governed by this delta 1, delta 2, delta 3. So, now we are saying that instead of working with the instead of assuming that there are operating on two floating sorry, I am going back. Instead of performing on the exact values a I j k, what I am saying is that I am going to operate on some perturbed values, and I am going to go through the exact same transformation equations, but I will assume that I am not introducing any additional floating point errors during the transformations, right. So, I am going to operate on some perturbed values instead of operating on the exact aij superscript k. I am going to operate on certain perturbed values, but I will assume that I will get the same results by performing exact operations on the perturbed values. So, the perturbations, however, are only applied to the elements belonging to the rows that are transformed by the step k, that is rows with index greater than k. So, basically I am saying that instead of operating on a I j k, I will operate on a bar I j k plus epsilon I j k. So, now I am going to get a bar I j k plus 1 is equal to a hat I j k minus a hat I k k divided by a bar k k k times a bar k a k j. A bar k, these have already been obtained, so they have superscript k, right. So, they have already been obtained from the previous step in the Gaussian elimination, right. So, these values are known. Now, what I am saying is that the values that I am going to transform, right, I am not going to operate on those values themselves, I am going to operate on those values plus some perturbed values, and I am going to assume that my floating point operations are not going to introduce any errors. So, I am going to get the exact solution by operating on these perturbed values and I am going to get the exact same solution. I hope that is clear, but basically the idea is that instead of looking at the effect of the floating point operations, we say that we are trying to get the same solution by considering perturbations in my original matrix components. So, I get some value after my operations, right. Those operations typically include floating point operations operating on the original numbers that were there on the matrix. So, I say that instead of operating on the original numbers on the matrix, I will operate on some original numbers plus perturbations, on some perturbed numbers, but during the operations I will not introduce any floating point operation, any floating point errors, and I want to get the same values as a result of this operation. So, the idea is that instead of we are transferring the problem to the perturbations. So, we want to find what perturbations in my original system will give me the same errors, same floating point errors as I would get during round off, right. So, what changes should I make to my original matrix elements in order to get the same error which I would have got due to round off. From this expression, m bar I k is equal to a bar I k by a bar k k 1 plus delta 1, we therefore get epsilon I k k is equal to a bar I k k times delta 1. How do we get this? Well, we compare this expression with with this expression, right. When we compare this expression with this expression, we get epsilon I k k is equal to a bar I k k times delta 1. Then we can rewrite this expression as this. This is just a question of substitution, right. We are going to substitute those values here and we get this, and finally substituting all this in this expression, we are going to get finally this expression, which you can see gives me an expression for the perturbation epsilon I j k, which gives me an expression for the perturbation epsilon I j k. So, that is the basic purpose of this exercise. The basic purpose of this exercise is to try to find bounds on the perturbation epsilon I j k, because we know that the perturbations are equivalent. The end result of the perturbations is going to be the same errors which would have accrued if I had the floating point errors, right. So, instead of trying to find bounds on the floating point errors themselves, I am going to try to find bounds on the perturbations. So, this is just I am transferring the problem of finding the bounds on the perturbations, because I am saying the end result of the perturbations is equivalent to the floating point errors in the operations. So, we get this, and then if we take bounds on both sides, we get an expression like this, and this must be lesser than or equal to. So, this is a bar I j k plus 1 times this term minus a bar I j k times this term. So, this has to be lesser than or equal to maximum of this and this times this term, right, because this is maximum of this and this must be larger than this minus this times this minus this times this must be lesser than the maximum of this and this times this minus this, right. So, this is lesser than that. So, we get the same expression I have rewritten here. So, mod of epsilon I j is lesser than or equal to max of this times this, and then we know that since delta 1, delta 2, delta 3 are less than the machine precision u. So, these must be small numbers. So, I can do a binomial expansion of this, and if I do that, I can write 1 plus delta 3 minus 1 as 1 minus delta 3, 1 plus delta 2 minus 1 as 1 minus delta 2, and this is approximately equal to delta 2 plus delta 3, where I have ignored terms which involve 2 deltas, delta 2 times delta 3. Similarly, so if I take bounds on that, I get this is approximately equal to mod of delta 2 plus delta 3, which is lesser than or equal to mod of delta 2 plus mod of delta 3, and since both delta 2 and delta 3 are lesser than u, this must be less than 2 times the machine precision. Similarly, the second term 1 plus 1 plus delta 2 inverse, I can write it as 1 minus delta 2, again using binomial expansion, taking into account the fact that delta 2 is very small, much smaller than 1, which is going to give me approximately delta 2. So, again I take bounds on that, this is going to be lesser than or equal to delta 2, and again delta 2 is lesser than the machine precision. So, that is going to be less than u. So, we finally get mod of epsilon I j to the power, not to the power, mod of epsilon I j at the kth step is lesser than or equal to max of this times 3 times u, where u is the machine precision. Let us recall this equation. This equation, which was my update formula for Gaussian elimination, and which says that a bar I j k plus 1 is equal to a bar I j k plus epsilon I j k minus this. If we sum this expression for k is equal to 1 to r, where r is the minimum of I minus 1 j, I being the row index, j being the column index, we are going to get sigma k equal to 1 to r a bar I j k plus 1 minus sigma k equal to 1 to r a bar I j k is equal to e I j, where e I j is basically I am summing this term from k equal to 1 to r, e I j minus sigma k equal to 1 to r m bar I k a bar k j k. This everything is going to cancel except the r except the term which is going to be for k equal to r, which is going to give me a bar I j r plus 1, and the term which involves 1 a bar I j 1. So, I have a bar I j r plus 1 minus a bar I j 1. The rest of the terms are going to cancel. The rest of the terms from this first term is going to cancel the rest of the terms from this second term. So, we are left with a bar I j r plus 1 minus a bar I j 1, but a bar I j 1 is going to be a I j, because that is the first that is the first step, and the first step there are no round off errors. So, a bar I j 1 is going to be equal to a I j. So, we can get an expression like Aij is equal to A bar ij r plus 1, changing the sides, right, bringing this to the left hand side. So, we get A bar ij r plus 1 plus sigma k equal to 1 to r m bar I k A bar k j k minus E I j. For terms at or above the principal diagonal, j is greater than or equal to I, and since r is equal to minimum of I minus 1 and j, if j is greater than I, so r must be equal to I minus 1, because r is minimum of I minus 1 and j. So, r is equal to I minus 1. So, in that case, A bar ij r plus 1 is going to be A bar ij I, because r is equal to I minus 1. So, this gives me A bar ij r plus 1 is equal to A bar ij I. For terms below the principal diagonal, the row index is going to be greater than the column index, I is going to be greater than j. Therefore, minimum of I minus 1, j is going to be j. So, r is going to be j. Hence, in that case, A bar ij r plus 1 is equal to A bar ij j plus 1, which we know from our Gaussian elimination is going to be 0. So, beyond the jth step, the A bar ij is going to be 0. The terms which are below the principal diagonal are going to be 0. Hence, we can write this previous expression. We can write it as Aij, which is equal to Aij1, is equal to A bar iji plus this term, which does not change. This is true for j greater than or equal to I, and this is equal to 0 plus this term when I is greater than j. So, basically I have split this equation into two parts, one for j greater than or equal to I and one for I greater than j. And if we assume that m bar ii is equal to 1, I can put this term inside the summation and change this index from k equal to 1 to I minus 1 to k equal to 1 to I. So, in that case we can write Aij is equal to sigma k equal to 1 to I m bar I k A bar k j k minus E I j, provided m bar ii is equal to 1. If that is true, then we can combine these two equations together to write Aij is equal to sigma k equal to 1 to p m bar I k A bar k j k minus E I j, where p is equal to minimum of I and j. If j is greater than I, then p is going to be I. When I is greater than j, then p is going to be j. So, when j is greater than I am going to recover this first equation. When I is greater than j, I am going to recover the second equation. So, I finally get Aij is equal to sigma k equal to 1 to p m bar I k A bar k j k minus E I j. So, in the above equation, we can see that only components m bar I k are needed when they are m bar I k terms. We only involve the m bar I k terms which are below the principal diagonal, and A bar k j terms which are above the principal diagonal. We can see, because k is equal to 1 to p and p is equal to minimum of I j. Here k is the second index, and k can be as high as only as p, and p is bounded by this. So, this term only involves terms which are at or below the principal diagonal, while here this term, since the first index is k and k can be only as high as p and p is bounded by minimum of I j. So, this term only involves terms which are above the principal diagonal. So, because of that, this equation only involves components of m bar I k at or below the principal diagonal and components of A bar k j k at or above the principal diagonal. Then, since we do not use components of m bar which are above the principal diagonal and components of A bar which are below the principal diagonal, we can assume them to be 0, in which case this expression is a LU decomposition. This is a lower triangular matrix, that is an upper triangular matrix. So, in that case we are going to get A is equal to L bar U bar minus E, where E is the matrix whose components are given by Eij. Let us go back to the previous slide. These components are given by Eij, and L bar is what we just discussed, is made of its components are M bar I k, and U bar has components A bar k j k. Thus, the computed matrices L bar and U bar are the exact triangular factors of the matrix A plus E. So, LU we thought was the triangular decomposition of A, right, but because of round off errors we are going to get L bar U bar, and L bar U bar is the exact decomposition of A, right, A plus E. It is the exact decomposition of A plus E. So, now we have transferred the error into a perturbation in A, right. So, A, the original matrix A plus some perturbation matrix E is going to give me L bar U bar. L bar U bar includes the effects of all the floating point errors. So, recall that we have defined Eij is the sum of all the epsilon ij k's. That is what we defined exactly here when we defined Eij is equal to sigma epsilon ij k, and R is equal to minimum of I minus 1 j. So, we can write this as the sum of minimum I minus 1 j quantities, and we also remember that epsilon ijk is has this bound which we obtained earlier. So, we can say that mod of Eij is lesser than or equal to 3u times minimum I minus 1 j times maximum of mod of Aij over k. Basically, we are saying that since this is bounded by that, right, and this is formed by the sum of these epsilon ij k's, then we get a bound on Eij which is 3u times minimum of I minus 1 times j, because this sum is over R, and R is minimum of I minus 1 times minimum of I minus 1 and j. So, we are taking this value which is the maximum value of R, right, R is bounded, R is given by this. So, this value times the maximum of all these sums, right. This is the maximum of Aij k, Aij A bar ij k plus 1, and that is maximum of A bar ij k over all the k's. So, we are taking the maximum possible. So, we have a sum of epsilon ij k which involve terms like this, right, maximum of this and this. So, we are looking at all the sums, and we are saying that we are going to take of all the terms which comprise the sums, we are going to take the maximum value, this maximum of all those values. So, that maximum value times I minus 1 is going to be an upper bound on mod of Eij. So, that is just the absolute upper bound, because we had this term comprises a number of sums. So, we are taking the largest term in that sum, and multiplying that by the number of terms in the sum. So, that is going to be greater than or equal to mod of Eij. So, again let me repeat, this term is a sum of a number of terms, right. we are taking the largest term in that sum and multiplying it by the number of terms in that sum, and we are saying that has to be a bound on the left hand side, which is the sum of all those terms. So, that was a bound on the left hand side. Let us consider a bound on the right hand side. Since the original system is of the form Ax is equal to b and the right hand side is transformed in remember, we recall from Gauss elimination, the right hand side is transformed in exactly the same way as the left hand side, right. So, the right hand side, because the right hand side is transformed in exactly the same way as the columns of A, we can develop a bound on the error in the right hand side, because we are performing operations on the right hand side every time. At every step we are operating on the left hand side as well as on the right hand side. So, when we operate on the right hand side, we introduce floating point errors on the right hand side, and these are the bounds on the, similar to the errors we get on the bounds and the errors we get on the bounds we get on the errors on the left hand side. We can similarly get bounds on the errors on the right hand side in a very similar fashion, and they have very similar form. So, mod of Ci is the it's the sum of the errors on the right hand side, and that is bounded by something like this, which is very similar to the bound on the error in the right hand side. So, introducing the intermediate vector y is equal to u bar x, we solve the system L bar u bar x is equal to b plus c, right. Now, L bar u bar include the floating point errors, right, plus b plus c. C, why do we have the c? Because c is because of the round of errors in b, right. So, this is the actual system that we are solving, and introducing an intermediate vector y is equal to u bar x, we get L bar y is equal to b plus c, and then we solve for y here. We solve for y from this equation, put y on the right hand side, and finally we solve for x. U bar x is equal to y. So, summarizing, we have obtained bounds on Eij and on the right hand side Ci, and these bounds have the following form. Now, it is clear that if these errors are going to be small, then these bounds, these bounding values must be small too, right. So, in order to bound these errors, these terms a bar I j k and b bar I k must be small. So, it is very important that the pivoting strategy, whatever pivoting strategy we adopt, should limit the values of mod of a I j k and b bar a bar I j k and b bar I k. But what is interesting to note is that these bounds do not involve the multipliers m bar I k. Thus, the magnitude of the multipliers has no effect on the magnitude of the round off errors during Gaussian elimination, because these terms do not involve the multipliers, they only involve the coefficients and the right hand side, the approximations to the coefficients and the right hand side, they do not involve the multipliers. We have thus far obtained bounds on the round off error in the elimination step, that is, we have obtained bounds on E, where E is equal to L bar u bar minus A. So, L bar u bar is the approximation to LU, LU is the exact decomposition of A. So, L bar u bar minus A is equal to E, right, that E matrix, and we have obtained bounds on the terms of the E matrix. Each term of the E matrix is Eij. So, we obtained bounds on the error matrix in the coefficient, and we have also obtained errors on C, bounds on C, where C is the error in the right hand side. So, we have obtained bounds both on the coefficient matrix as well as on the right hand side. Errors due to round off, we now know that those errors due to round off cannot exceed these bounds, right. So, those errors due to round off cannot exceed these bounds. We have found bounds on those errors. However, the full solution of the linear system also involves a back substitution following Gaussian elimination. So, this is the bound on the errors due to Gaussian elimination. There will be additional errors due to back substitution which follows Gaussian elimination. However, for most matrices that occur in practice, the round off error due to back substitution is negligible compared to the round off error due to Gaussian elimination. Thus, the errors E and C during the elimination step limit the accuracy of the computed solution Ax equal to b. So, the most of the errors, round off errors, occurred during the elimination step, and if we obtain bounds on those errors, whatever additional errors accrue during back substitution, they are going to be negligibly small compared to, they are still going to be bounded by the bounds which we have obtained during for Gaussian elimination. So, let us look again at those bounds. Mod of Eij less than or equal to 3 times the machine precision u times minimum of I minus 1 j, then maximum of a bar I j k over all the iterations k. Similarly, mod of Ci less than or equal to 3 times machine precision u times I minus 1 times maximum of b bar I k over all the iterations k. These are basically what are known as posteriori bounds. Why? Because we cannot predict those bounds before we have actually computed these values, right? Because these values are the maximum over all the steps in the Gaussian elimination. So, unless we have actually gone through the steps of the Gaussian elimination, we do not know what these max values are. We do not know what max k a bar I j k is or max k b bar I k k is. So, these are posteriori bounds, and these can only be obtained after we have performed the Gaussian elimination. However, it is desirable to obtain a priori bounds, that is, we want to know what my error will be. I want to know what the bounds on my error will be before I have actually started doing the computations, right. So, a priori bounds are always more useful than posteriori bounds. So, let us see how we can obtain a priori bounds on the error in Gaussian elimination. It has been shown that a priori bounds can only be obtained if mod of m bar, I will not go into the derivation for that, but let us take it for granted. It can be, there are references, and the references I have referred to in this course, you can find discussions on this. So, it can be shown that if mod of m bar I k k is always less than or equal to 1, then we can obtain a priori bounds. But when is mod of m bar I k k going to be less than or equal to 1? When are those multipliers going to be less than or equal to 1? They are going to be less than or equal to 1 only when we have performed pivoting, when at least we have performed partial pivoting, right. At every step we choose the largest element in a column as the pivot. Only then can we be assured that the multipliers that we are going to use are always going to be less than or equal to 1, and in that case we can obtain a priori bounds. So, in case we perform partial pivoting, then we can show that mod of Eij now it changes. So, the bound changes, the bound becomes narrower. Instead of this less than or equal to 3u times this, now we are going to get this less than or equal to 2u times minimum of I minus 1 j, but most interesting is this part. Let us look at what this was. This was maximum of a bar I j k over all the steps k, right. So, now instead of that I have maximum of a bar I j k over I j k. So, not only is the maximum over the steps k, it is over all the elements of the matrix, right. It is over all the elements of the matrix I j k. So, now I am saying that mod of E I j is lesser than or equal to the largest value in the coefficient matrix, not only over the steps, but over each element. Not it is not only concerned with each element, it is a maximum of over all the elements in that matrix. It is a maximum of I j as well as k. So, it is not only a maximum of over the steps, it is also a maximum over the row and column indices. So, basically it is the maximum absolute maximum element in that matrix over all the steps. It is the maximum element in that matrix over all the steps. So, the last factor on the right is computed as maximum of I j mod of a bar I j k. So, at each step k, we find the largest element in the matrix and then we find the largest over all the steps. So, maximum of k over I and j. So, if we can bound this computed value in terms of some a priori values, then we can obtain an a priori bound on the round of error. So, if we can bound this in terms of some a priori values, in terms of some values which are known, which are known before I do my Gaussian elimination, typically some values which are part of my original matrix A, right. Using some components of my original matrix A, if I can obtain a bound on this, I am going to get an a priori bound on my error due to Gaussian elimination. To do that, let us denote Gn is equal to maximum of I j k mod of a bar I j k divided by maximum of I j mod of a I j. If we do that, we can write this expression, we can rewrite this expression as mod of E lesser than or equal to 2u, 2u remains the same, maximum of a bar I j k I j k, I am going to replace this by Gn times maximum of I j mod of a I j. So, that is going to be Gn times maximum of I j, and what is this matrix? This matrix is nothing but minimum of I minus 1 j. So, for each element I have computed, I have obtained this element by taking minimum of the row index minus 1 and the column index. So, the row index here is 1, the column index is 1. So, 1 minus 1 is 0, 0 and 1, minimum of 0 and 1. So, that is going to be 0. Similarly, I have computed all the rest of the terms in this matrix, right, which is nothing but minimum of I minus 1 and j. Elements of the matrix on the right hand side are each given by minimum of I minus 1 j. Hence, the matrix norm of the matrix, the maximum norm of the matrix is given by the sum of the elements in the last row. Recall what is the maximum norm? It is the sum of the elements in each row, maximum of that, right. So, I have taken that my last row is going to contribute that, and that is going to be 1 plus 2 plus 3 plus n minus 1 plus n minus 1. I have grouped these terms together. You can see these are the sum of the first n natural numbers, which is given by half n n plus 1. So, this is half n n plus 1 minus 1. So, we get mod of E infinity. Why have we taken E infinity? Because we have computed the infinite norm of this matrix, right. So, mod of E infinity is lesser than or equal to 2u Gn times max I j over mod of I j. This term remains the same, and then the infinite norm of this matrix, which we just calculated to be half of n square plus half of n minus 1. By slightly refining the estimate of E, which I am not going to go into again, it is a slight change actually, we can show that mod of E infinity is lesser than or equal to 2 u g n max I j mod of I j times half of n square. So, it is actually, here we have obtained half of n square plus half of n minus 1, actually it is less than half of n square. This is a sharper bound, right. It can be shown that we can write it like this, and then 2 cancels out, we get n square g n u maximum of I j mod of I a I j, but maximum of a mod of a I j is lesser than or equal to the infinite norm of my original coefficient matrix. Why? Why? Because the infinite norm is defined as sum of over all the columns, sum of each row, sigma j equal to 1 to n mod of a I j, and then the maximum of that, right. So, maximum of I j mod of a I j is going to be bounded by the infinite norm of A, right. So, I can replace this on the right hand side by the infinite norm of A, because this is greater than that. So, I finally get this mod of E infinity is less than or equal to n square g n u times A infinite norm of A. But we still have this factor g n, right. What is this factor g n? Let us recall, g n we define to be this, we define this factor g n to be this. And it can be, it has been, it can by just by solving a large number of problems, finding out what the typical values for g n, it has been shown that for partial pivoting, g n is less than or equal to 2 to the power n minus 1, where n is the dimension of the matrix, and for complete pivoting, g n is less than or equal to 1.8 to the power 0.25 ln n, which gives a narrower bound. But even if we do just partial pivoting, this bound is sufficiently narrow because g n rarely exceeds 8, right. So, the bound on E is satisfactory because g n is usually quite small, g n rarely exceeds 8, g n rarely exceeds 8. So, in that case we have obtained bounds on E bar, on E. L bar and U bar are the computed triangular factors with partial or complete pivoting. Why do we say partial or complete pivoting? Because we have tried to find a priori bound, right, and we have mentioned that we can only obtain an a priori bound when all those multipliers are less than 1. So, partial pivoting is necessary. So, this bound is satisfactory unless the ratio g n is large. So, that was so we have found a bound on the Gaussian error in Gaussian elimination due to round off. Some people have often tried to improve the solution, improve the results of Gaussian elimination. They often try scaling. Basically, they either scale the coefficient matrix or they scale the right hand side, and they sometimes think that because they are doing scaling, they are somehow going to get better solutions, they are going to get smaller errors. But it has been seen that scaling the unknowns or the coefficient matrix has no effect on the accuracy of the computed solution except by affecting the choice of the pivots. So, it can improve the stability of the solution because pivot is going to, the size of the pivots is going to determine the stability of the solution. So, if the pivots are large, we are going to get more stable solution. If the pivots are small, the solution is going to be less stable, but it is not going to affect the accuracy of the solution. The accuracy of the solution is not going to be affected by scaling. So, that was a discussion on the error estimate due to round off during Gaussian elimination. From next lecture onwards, we are going to talk about iterative methods for solving linear systems. But before we talk about iterative methods, for instance Gauss-Seidel iterations or Jacobi iterations, we will briefly talk about a simple technique to improve the solution of direct methods, improve the solution obtained using direct methods such as Gaussian elimination by some iterations. So, we solve the problem using Gaussian elimination, but then we can improve the solution by doing some simple iterations. So, we will talk about that first before going into directly into iterative methods for solving linear systems, and we will find that these iterative methods are particularly suited for problems which have coefficient matrix which are very sparse, right, which are very sparse, because Gaussian elimination, we know one of the problems with Gaussian elimination is that it destroys the sparseness of the system, right. So, we want, for if the matrix is really sparse, we want to use iterative methods because those methods preserve the sparseness of the system. So, we can take advantage of the sparseness in reducing the number of mathematical operations as well as the storage required. Thank you.